To understand color as it pertains to video games, you're going to need to understand a few things about binary, hexadecimal, and decimal. Let's start with a numbering system you already understand, which is decimal. Decimal contains 10 digits. It's a base 10 numbering system, which means it's based on the 10 digits, ranging from 0 through 9. When we count in decimal, we start with 0 and we increment by 1. When we reach 0, we add a new column to the left side of the previous column. In decimal, this new number is 10. Then we continue to increment. When we run out of digits again, we add another column. After that, another, and infinitely we have as many numbers as we ever need. Computers count a little differently. Computers use base 2, or binary. This means that their counting system only contains 2 digits, 0 and 1. This is because computers use electricity, and electricity can really only be in one of two states. Consider it like a light switch. When the light is off, binary is 0. The room is dark. And when the light is on, binary equals 1. The room is now illuminated. Similar to how we count in decimal, when we run out of digits for the first column, we add another column. Then we add another column and another column. However, you'll notice we quickly run out of digits. So what happens is each new column equals a multiple of the previous column. Counting in binary is really just a lot of math. You don't have to worry though, the computer does it and you don't have to. The first column in binary equals 1. After that, the next one equals 2, then 4, 8, 16, 32, 64, 128, and so on. You'll notice here that we now have 8 columns. For a computer, this is known as 8 bits. A single bit is a single column in binary counting. 8 bits equals 1 byte. If you're familiar with classic games, you may have heard the term 8-bit a lot. This is because classic games ran on processors that were only 8 bits. This meant that they only knew numbers up to 255, which is actually 256 numbers, including the 0. This is why a lot of retro games had lives capped at 255, or levels capped at 255. It was just the largest number a computer could count to. Take, for instance, Pac-Man. After level 255, Pac-Man gets kind of glitchy because the computer can't count past 255. Nowadays, most computers are 64-bit, which means we can count to a ridiculously high number. But for the purposes of understanding color, you really only need to know 8 bits. Here are some binary numbers converted into decimal numbers. All the computer is doing is checking which bit is on and which bit is off, and then adding the associated numbers. There's one more counting system you might need to understand, and that's hexadecimal. Hex for 6 and dec for 10. This is a base 16 counting system. That means there are 16 digits, ranging from 0 to F. Unfortunately, the world only counts through decimal, so we ran out of digits at 9. So for hexadecimal, we started using letters. So we made A equal 10, B equal 11, C, D, E, and then F equaling 15. Here's what it would look like to count in hexadecimal. You can see it works the same way as decimal and binary. Once you run out of digits for the first column, you just go into the next column and start again. You might be wondering why we even use hexadecimal. Well, if we go back to our 8-bit binary number, we can actually split this up into 2 halves. We can put 4 bits on one side and 4 bits on the other. Each grouping of 4 bits is called a nibble, and one nibble is a single hexadecimal digit. Here's what it looks like to convert some binary numbers into hexadecimal numbers. If you've ever worked with color on the web, this might look familiar to you. However, you may have seen 3 hexadecimal numbers linked together, and it might look something like this. This hexadecimal number actually equals a color. That might sound a little abstract, and actually it is. Computers don't understand color, but we needed a way for a computer to translate numbers into a color. Let's wipe this clean and start fresh. The human eye picks up color with 3 different cones. These are receptors in the eye that pick up 3 different wavelengths for color. We have one for red, one for green, and one for blue. If you look at a rainbow, you'll notice that red is all the way on one side of the wavelength, green is somewhere in the middle, and blue is off to the shorter wavelength. This is how we're able to see the rainbow we see. Because we understand this, we created monitors and televisions to pretty much do the same thing. Each little dot on the screen of your television or monitor contains a certain amount of red, green, and blue. And depending on how much is contained in each little dot, it creates a color. Now multiply these dots by an entire resolution, and you get an image. And you don't even see the dots. Each little dot of an image is called a pixel. This is kind of a portmanteau of the words picture and element. It is the smallest unit we can measure for an image on a computer. But let's get back to red, green, and blue. Each one of these colors, or hues, takes up a channel on your computer. And each one of these channels actually contains 1 byte, or 8 bits. Your computer provides 8 bits for red, 8 bits for green, and 8 bits for blue. This totals 24 bits. This is known as true color. If you calculate the total amount of colors you can get from these combinations, it's over 16 million different shades. It's estimated that the human eye can only see somewhere up to 10 million shades. This is why we call it true color. It simulates real life fairly well. If you've ever messed around with color settings, you might notice that colors are actually 32 bits and not 24. This is because there is actually one more channel. This channel is known as alpha. Alpha doesn't measure the color. Alpha measures the transparency of the pixel. While red, green, and blue mix together to create one color, the alpha channel is used to make that pixel more opaque or more transparent. This is a very important channel to understand. The alpha channel has allowed us to layer images. So you're probably wondering now, how do we turn all this binary and hexadecimal and decimal into all the colors we see? Well, it's very easy. Since we know that each color channel is only 8 bits, we know that it can have a number from 0 to 255. So to create any color other than red, green, and blue, we just mix these values together. The number 0 will represent no intensity for that color. That color does not exist in this pixel. 255 will be the max amount of intensity of that color. For the alpha channel, 0 means no opacity. So this pixel will be technically invisible. 255 on the alpha channel means that this pixel is completely visible. There is no transparency. At this point you might be wondering, alright, this is great, but how does this relate to GameMaker Studio? Well, GameMaker Studio has built-in variables for colors. I'll list a few of them here. However, you'll probably want to use your own colors. And I find one of the best ways to make your own colors in GameMaker Studio is to use a built-in function called MakeColorRGB. When you use this function, it'll ask you for 3 different arguments. And what is it looking for? Well, it's looking for the red, green, and blue channel, and it's looking for a number between 0 and 255. However, if you understand hexadecimal better than decimal translated from bits, you can actually use those as well. Here are a few examples of hexadecimal colors in GameMaker. I hope now you understand how GameMaker Studio uses color, and how your computer turns electrical signals into a language your monitor can understand, and then display as different colors per pixel.